going to be the start of our fluid mechanics unit, and we're going to start out with some basics that we need to know, and that's how volume, mass, and density are related. So density, the letter they use for it is the Greek letter rho. They don't use D, all right? It kind of looks like a curly P. And density is mass divided by volume. Now, we might rearrange this. A lot of times we're trying to find mass, so mass would be density times volume. So we're going to use that quite a bit. I'm going to give you the density of water is equal to 1,000 kilograms per meter cubed. And that seems like a lot, but a meter cubed is an awful lot of water, and that much would weigh 1,000 kilograms. Now, a note about finding area. About finding volume. I'm going to do an example here. Let's say we have a cylinder. Okay, and it has a radius r and a length h. The volume of the cylinder is pi r squared h. Now you'll notice something. This part right here, pi r squared h, is the area of this circle. So another way of finding the volume would just be volume is area times height. And that will work for many different, or all different shapes. Now, I'm going to give you an example up here. I'm going to write it in green. You don't have to copy it, but I want you to see how it works for, say, a rectangular prism. Okay, I'm going to call this side the length, that the width, and this the height. Now we know that volume is equal to length times width times height. This part right here is the area of this square. So this is area times h. So area times h is a way to find volume that you're going to use sometimes. Now here's an example. What is the mass of water in a tank which has a bottom with an area of 100 meters squared and a height of 3 meters? Kind of sketch it over here. We have the area of the bottom of this thing is 100 meters squared. We're going to have a height of 3 meters. And we want to find the mass of water. First, we're going to find the volume. Volume is A times H. It's 100 meters squared times 3 meters. And that's going to give me 300, and meters squared times meters is meters cubed. Okay, then our next step is to find the mass. Mass is equal to density times volume. So that's going to be 1,000 kilograms per meter cubed. The density of water times 300 meters squared. And that's going to give me 300,000 kilograms for the mass. Now, a lot of times when dealing with fluids, we're going to talk about the pressure, and here's kind of a morbid example of how force and pressure are related. I have 200 kilogram masses placed on 2 students as shown below. Which one is more likely to be injured? We'll call this one A, we'll call this one B. Now, the force is the force of gravity on this. It's 2,000 newtons. The force for B is 2,000 newtons. So it's the same amount of force, but if we look at it, it's going to be pretty obvious that B is more likely to be hurt. A, the force is spread out over a larger area, and B, it's concentrated just in just one point, in a very small area. Okay? So we're going to come up with this idea that pressure is force divided by area. So even though the forces are the same, the smaller the area, the greater the pressure. Okay? And then the units, okay, pressure we know is in pascals, equals newtons for the force divided by meters squared. So a pascal is the same as a newton per meter squared. So, top of the next page, we're going to have an example. All right, at a depth of 20 meters in the ocean, the pressure difference between the inside and the outside of the sub is 2 atmospheres. The window of the sub is a square. It gives you the dimensions, and then what is the force on the window. So the first thing, we're going to say that the pressure is 2 atmospheres, is 2 times 10 to the 5th pascals. Now, if I think of this window, it's 10 centimeters on a side. Now I have to convert that, so I move it two places, so this gives me 0.1 meters and 0.1 meters. So the area is going to be 0.1 meters times 0.1 meters, 0.01 meters squared. And then I'm trying to find the force. The equation is P equals F over A. If I rearrange this, I'll get F is P times A. So the pressure was 2 times 10 to the 5th. The area was 0.01, and that's going to give me a force of 2,000 newtons. Now you'll notice here that as the area goes up, the force would go up. That's why they tend to make sub windows small, because if I have a smaller area, I have a smaller force, and it's less likely that the window is going to get broken open and water start pouring in. Now, pressure and depth. This is pretty obvious, okay? As you go down in a fluid, pressure increases. Okay, if you ever swam deep in a diving pool or in a lake, as you go down, your ears start hurt because you're getting more pressure. It's because the pressure is due to the weight of the fluid above. Now, our equation for this is going to be the pressure where you are equals the original pressure plus or minus rho g h. It's plus or minus because if I'm going down, pressure gets greater. As I'm going up, pressure is going to get less. So what is the air pressure for a plane at an altitude of 10,000 meters? It gives us the density of the air there. All right. So we're going to start this way. When I'm on the ground, the pressure is 1 atmosphere. So 1 times 10 to the 5th pascals. Okay. And then we're going to find a new pressure. So P is P0 plus or minus rho GH. P equals 1 times 10 to the 5th plus or minus 0.65 times 10 times 10,000. Now, which do we want, plus or minus? Since we're going up, we want to use the minus. Okay, because the pressure is going to be lower the higher up I get. So we're going to change this to a minus sign. So this gives me 100,000 minus 65,000. So the pressure is 35,000 pascals. Now, if I wanted to just get a way to compare it, that's 0.35 atmospheres. So the pressure is only 35% of what it is on the ground. And that's why planes are pressurized. When you go up into a plane, they keep the air inside. It's completely sealed. The air is at 1 atmosphere, so you can breathe normally. And that's why they say if they lose cabin pressure, say somehow there was a hole punctured inside of the plane, the oxygen mass dropped down because at 0.35 atmospheres, you wouldn't be getting enough oxygen. Now, pressure gauges and gauge pressure. So here is a simple pressure gauge. So I have here a container at pressure 1. I'm going to put a tube in there and connect it to another chamber that's at pressure 2. Okay, and let's say we put some liquid in the tube and it does this. Okay, it's higher on the 2 side than the 1 side. Where's the pressure greater? The pressure is greater in 1 because it's pushing the fluid down and making it raise up on the other side. And this difference in height right here we can use that to find the difference in pressure. So I would get something like this. Pressure 1 equals pressure 2. It's going to be, pressure 1 is going to be greater than pressure 2. So we'll do plus rho GH for that. Okay. Now, pressure 1 minus pressure 2 would be rho GH. This is delta P. It's rho GH. This difference in pressure is called the gauge pressure. So what a pressure gauge can tell you is not actually specifically what the pressure is where you are, but what the difference in pressure is between two different places. And normally, one of the pressures is going to be 1 atmosphere. Okay, so the gauge pressure is going to be the difference between 1 atmosphere and where you're located. Top of this page. So here's an example. We have a sub at a depth of 90 meters. It has a window which has an area of 0.03. And we want to know the pressure outside of the sub, the gauge pressure, and then the force. So I'm going to draw a little picture here. So here we have the ocean, okay, at a depth of 90 meters. Okay, we have a sub. Okay, there's our sub. All right, and I want to know what the pressure down here is. Well, it's going to be greater than it is because we're going down to the water. Greater than what? We have to compare it to something. Well, the pressure right up here is 1 atmosphere. Okay, because it's open to the atmosphere at the surface of the water, and then we've gone down. So we're going to use this equation, the P equals P0 plus rho GH. I'm picking plus because I know the pressure is going to be greater, and P0 is going to be the atmospheric pressure. So P equals 1 times 10 to the 5th plus, it's in water, so we're going to use 1,000 for the density. G is 10, and then our difference in height is 90. When we do this, I'm going to get 100,000 plus 900,000 equals 1 million pascals, which is 10 atmospheres. Okay, so that's a pretty big pressure. Now the gauge pressure, P, well, inside the sub, the pressure is equal to 1 atmosphere. Okay, the pressure outside the sub, it is equal to 10 atmospheres. Gauge pressure is the change in pressure, the difference in pressure between the inside and the outside. So that's going to be 9 atmospheres. Just subtract them, or 900,000 pascals. Now part C is what is the force on the window going to be. We have the area up here is 0.03. So we're going to do P is F over A. So then F is P times A. Now we have to figure out what pressure we're going to use. Are we going to use 1, are we going to use 10, or are we going to use 900,000? Now it turns out that here's what's happening. Okay, if I have the window with a sub, all right, I have a pressure pushing inward of 10 atmospheres. I have a pressure pushing out of 1 atmosphere. Okay, the net pressure on that is going to be 1. Or, sorry, not 1. It's going to be the gauge pressure. It's going to be 9. So that's the pressure I'm going to use in here. So this is going to be 9 times 10 to the 5th. And then the area was 0.3. So that's going to give me a force of 270,000 newtons. Okay, we're going to finish this off doing Pascal's principle. We're going to kind of define it 2 ways. One is that force is transferred undiminished through a fluid. And what that's going to end up meaning is that if 2 points are at the same height, we'll have the same pressure. Now that's only true for a static fluid. We're eventually going to start dealing with moving fluids, and that's not going to be true. But if it's a static fluid at the same height, we'll have the same pressure. Now here's an example of where this comes into play. It's a hydraulic jack. Okay, hydraulic jack, you can use a pretty small force to lift something kind of heavy. So we're going to try to lift this car over here at B by putting a force at A. We need to figure out how big that force is going to be. So that's going to be what we're looking for, is the force there. Now, because of Pascal's principle, we know the pressure at A is equal to pressure at B because they have the same height. Okay, now we have to relate this to force. Are we going to relate it to force? Pressure is force over area. So I'm going to have the force at A over the area at A is going to equal the force at B over the area at B. We're looking for the force at A. The area at A is 0.5 equals the force at B. So now what do we have for this thing? We know that the mass of the car is 400 kilograms. That means there's going to be a force of gravity here of 4,000 newtons. So the force at B is going to be 4,000 over, and the area at B is 2. If I cross multiply, I would get 2 times the force at A equals 0.5 times 4,000 is 2,000. So the force at A is going to be 1,000 newtons. Okay, so the force was actually quartered. Okay, the force at A is only 1,000 to lift a weight of 4,000 newtons. It's because the area was a quarter as big.